In a previous video, we've been looking at how to build variable input length PRFs, and we looked at kind of a high-level design given a compressing function or a hash function in particular, and a fixed input length PRF of combining these two together to build a secure variable input length PRF. And you'll recall the construction there was to hash the input down from its big size down to some n-bit string if n is the domain, the size of strings in the domain of the underlying small PRF, and then to run that string through the small PRF and to take the resulting output as the output of the big PRF. And we showed that the security of that construction relies upon being unable to find collisions, two inputs to the construction that would cause collisions in the hash function. There's an easy proof that that construction works from collision resistance, and we saw in the previous video that there's also a proof that's just slightly more clever that allows you to use a weaker kind of collision property on the hash function called epsilon almost universality. Today I want to take a look at two constructions that are common in practice. CBCMAC, so this is a variable input length PRF that just starts from just a block cipher, or just a more generally just a function family from n bits to n bits. And a construction called HMAC, which uses hash functions but uses them in a way that's very amenable to practice, in particular to using existing implementations of hash functions just off the shelf. HMAC in particular is very common in practice. CBCMAC is not seen in practice directly, but there are variations that we'll cover today that are in fact used in financial standards and other places. So these are the two constructions of variable input length PRFs we're going to consider today. To begin, let's look at what I'll call plain CBCMAC. So given a function family E that takes some keys k from this key set, that maps n-bit strings to n-bit strings for every key k, this is the CBCMAC construction. And it's called CBCMAC for obvious reason if you know CBC mode encryption. We're doing cipher block chaining still, but rather than returning the outputs of every block as part of a ciphertext, we simply do the chaining, not passing anything to output, just chain all the way through, and then it's the very last block cipher call that is output as the tag. And so as you can see, this is now a function that's secretly keyed, and it compresses strings that are multiples of n bits long down to a string of n bits. So here's sort of a more formulaic way of saying that. We've got this construction CBC over E sub k. It maps strings that are multiples of n bits to strings that are n bits long. And in what follows below, we'll drop the explicit reference to E and just call CBCMAC sub k. This is an instance of a function family CBCMAC whose key set is the same as the key set for the underlying block cipher, and it has the domain and range that we just described for each key. Okay, so let's say that you wanted to prove, let's say you didn't know anything about the CBCMAC construction, but you just had the intuition that, I think actually this thing works. In particular, what if you tried to prove that if E, the underlying block cipher, is a good PRF, then this construction is a good PRF too, but now on a much bigger domain. So in other words, if E is a secure PRF, and here I wanted to be clear about what I mean when I make this informal statement secure. What I mean is that if one considered every attack in the PRF experiment against E, so E is a secure PRF, so if every attack which uses parameters t, q, and mu, the running time, the number of queries to the oracle, these having total length mu. If every adversary, even the one that maximizes this advantage, where t, q, and mu are reasonable, if every such adversary with these resources gains small advantage, then that is what we mean when we say informally that E is a secure PRF. So we'd like to show that if E in fact is a secure PRF, then this construction, CBCMAC over E, is also a secure PRF. So how do we do this? Well, the obvious thing to do is to say, all right, let's see if we can get to the point of not thinking about the security of CBCMAC over this underlying block cipher. We'd really like to think about CBCMAC structurally. So if we were to replace the block cipher with, say, a random function, would it be the case that this construction is a good variable input length PRF. And the way that we get there, the way that we get rid of E sub k in this picture and replace it by rho, is by considering how we would take an attack against this construction and turn it into an attack on the underlying block cipher. Yeah? That's just going to be building a PRF attack for the block cipher. So here's what you would do. You build an adversary B. It's trying to win the PRF game and attacking E. Given access to an adversary A that supposedly is good at distinguishing this construction from a random function whose domain and range are the same as this construction. So we're building a B that will ultimately be dropped into the PRF experiment for E. And the way we do that is, well, as a rule of thumb, and I've said this before, when you're building your adversary B, in this case for the PRF experiment, try to build it so that if the oracle behaves like the real object, in this case E sub k, then what you simulate for A is the real construction. This is almost always the right way to go. So let's do that. Adversary B is going to run A. When A makes a query, and I'm reminding you here of the domain that these queries must lie in, and we know that A is not going to ask things outside of this anyway because those would be pointless. When A asks a query X, we simulate CBCMAC, so the construction in the picture, using our oracle, this O, our oracle, anywhere that we would be calling this square. We simulate CBCMAC calling our oracle everywhere there's a square on the X that we're provided. We're going to take the resulting output T and return that to A. When A halts with an output D, well, D prime I'm calling it here, we'll return D prime as well. Why does this make sense? Well, if B's oracle, when it's placed into the PRF experiment for E, if the challenge bit here is equal to 1, that means its oracle is this, in which case this perfectly simulates the construction in the picture. So if A outputs 1, meaning it believes it's been interacting with this picture, then we should output 1 as well, because this picture is perfectly simulated when our oracle is this. So we'll output 1. And in fact, what happens when the bit here is 0, meaning that we have this behavior? Well, we don't get this construction. What we get instead is this construction, but everywhere there's an E sub k, it's been replaced by a rho. So we'll see where that pops up in just a second. So as we just said, if we now consider for this adversary B, were it to be dropped into the PRF experiment attacking E, how well would it do? Well, we know that the PRF advantage is just twice the probability that B manages to guess the bit in this experiment, meaning the value of the bit that's in this oracle. So we just think about that piece because we're just going to scale it by 2 and subtract 1. And as we typically do, we break that probability into 2 pieces, where those 2 pieces are conditioned on the value of the bit that's determining the behavior of this oracle. As we've just talked through, when this oracle is E sub k, meaning that the bit in the PRF experiment that B is participating in is 1, then we perfectly simulate for A an oracle that gives this construction. So that's A given this construction. The PRF experiment outputs 1 precisely when we guess the bit properly, which in this case means outputting 1 ourselves, and our B does that precisely when A outputs 1. So we have this equality here. For the other half of B's PRF advantage in attacking E, our bit is 0 in the oracle, which means this thing is rho. We do the usual thing of, rather than thinking about, so the experiment outputs 1 when, in this case, when B would output 0, which means A outputs 0, but let's keep everything consistent. So we do the usual trick of just saying, let's change this into 1 minus the probability that B does not guess the bit correctly, which in this case happens because the bit is 0, happens when B outputs 1, which is exactly when A outputs 1. So we have these 2 expressions. We have this expression here and this one here, because the oracle that we simulate, as we said, when our bit up here is 0, meaning we have rho, is CBCMAC, well, with some abusive notation, CBCMAC sub rho, meaning take this picture and everywhere there's an E sub k, replace it with a rho. That's what happens in this case. So when we take these 2 pieces and drop them back into the PRF advantage for B, we get this expression, which is just twice the probability that B wins its experiment, and that's been conditioned on the challenge bit here. So we know that there'd be a half sitting out in front of each of those two conditional probabilities, that being the probability that the challenge bit in B's oracle is either 1 or 0. And we can replace those two conditional probabilities by the two expressions we just derived. Well, if you multiply through by 2, that gets rid of the halves. This +1 and this -1 cancel, and so what we're left with is the difference of these two probabilities. Okay, well, this piece here is useful because this is part of what we're looking for when we're thinking about A's advantage, right? A is supposed to be good at distinguishing this kind of an oracle, CBCMAC, with the key case, the actual construction of the picture, from an oracle that's a big random function, meaning one that has the same domain and range as the CBCMAC construction. But we're not comparing those in this expression. What we're comparing instead is the thing we care about, CBCMAC, versus CBCMAC, the picture with E sub k replaced by a row everywhere. What we really want is to have this oracle be capital R, a random function with the same domain and range. So what we do is we drop in here a 0, effectively. And we've done this trick before. So we subtract and add the same probability, having the net effect of adding 0, and that probability is the one that we're looking for. So in particular, we subtract the probability that whatever A it is we've been provided would output 1 if its oracle was a big random function, and then we add that probability right back in. And by doing this, we can drop parentheses around these two and around these two. Because what do we notice? The difference of these two is precisely A's PRF advantage in attacking CBCMAC, because A is supposed to be good at distinguishing CBCMAC from a big random function. So this is precisely the PRF advantage of A in attacking CBCMAC. So that's good. So we've at least tied together B's advantage in attacking E with A's advantage in attacking CBCMAC. We've got this extra piece here. So we're going to address that in just a second, but if we were to rearrange these terms, then what do we get here? By rearranging, if I just grab this minus term here and pull it over to this side of the equality, what I get is that the pure F advantage of A in attacking CBCMAC, so this piece here, is equal to the pure F advantage that this B that we've constructed in attacking the underlying block cipher E, plus this structural term. This is the term that tells us, even in the best case where we replace E sub k by rho everywhere, how easy is it to distinguish this construction with rows from a big random function? This is the structural term that we often talk about. So we have here a binding between however good A is at breaking CBCMAC with how good B will be, the one we just constructed, at breaking E. And the binding between them is a good one. It's tight if we can argue that this term is small, and in particular small for every efficient adversary A. So we have to answer that question. Is it the case that for every A? Because keep in mind, this reduction we just gave says, I don't care what A is, just give it to me and I'll run it. So for every A, there exists a B, in particular the B described by the pseudocode. So if I can provide you an A that's efficient, that makes this term large, something close to 1, it doesn't violate anything that we've done so far. It just says that, yeah, given that A, you can build a B for the PRF experiment. But it kind of doesn't matter how good B is at breaking the underlying block cipher, because by virtue of the fact that this term is large, that would mean that, in fact, the CBCMAC advantage that A gets is going to be large. In other words, if I can give an A that does an efficient A that does a good job of making this difference of probabilities large, then that same A will get large advantage in attacking CBCMAC, in which case CBCMAC is not a good variable input length PRF, no matter how good E is. In fact, that is the case. There's a very efficient A that gets large difference of these two probabilities. In other words, an A that does a good job of distinguishing CBCMAC with rho everywhere from a big random function. And here's that A have it make exactly 2 queries. So it's extremely efficient. The first query is 1 block long. It just asks the all zero string, and it receives a value t in return. So if we look at this picture, it's putting in all zeros here, and it's seeing this value here. This is t. For its second query, it takes that same 0 to the n, and it makes concatenates to the end of that the value t that it previously received, and it gets back a t prime in return. So this is 0, which means this value here is t, the thing we just saw as a result of the first query. T XORed with, well, this second block is also t, which means this is zeros. But zeros is what went in over here, and t came out, which means 0 going over here means t comes out. And so t prime, the result of processing this 2-block message, will be exactly the value we saw previously from processing this 1-block message. So if, we're looking at this structural piece here, if the oracle is this, CBCMAC sub rho, then A will output 1 with probability 1. In particular, when those 2 outputs, t and t prime, are the same, that's when A outputs 1, and that happens here all the time. How about in this case, that same A, if it asks those 2 queries to a big random function, well, those 2 strings are different strings. One of them is n bits long and one of them is 2 n bits long, which means the 2 values returned by this oracle will be uniformly random n-bit strings. So no matter what the original value with the first value t is that's returned, the probability that the second t prime is the same as that is simply 1 over 2 to the n, because the values returned are uniformly random n-bit strings. So we've just exhibited an A that is very efficient. It makes 2 queries, these totaling a length of 3 n bits. The running time is a constant times the bit length, in particular a constant times this. It's an extremely efficient adversary that's going to make this thing into 1 minus 1 over 2 to the n, right? So if we just plug in the numbers here, the period advantage of B plus 1 minus 1 over 2 to the n, and in fact, that A will also get exactly the same advantage in the big PRF experiment for the construction, because that attack we just gave works. Whether or not this construction is using E sub k under the hood, or this construction is using rho under the hood. There was nothing about the block cipher, about E, that we actually exploited. We simply exploited the structure. So likewise, this is going to become 1 minus 1 and 2 to the n, which tells us really unsatisfying result that we built this B, but for this particular A, the advantage that B gets in attacking the underlying block cipher is 0. Because, in particular, the attack exploited nothing about the block cipher itself. It only exploited something about the structure. But nonetheless, I thought it would be useful to go through this. We could have seen that attack already, but I thought it would be useful to go through this just as a way of seeing that you can, even if there's an attack, always start to write down a proof by following the steps that you know from previous efforts. And you'll reach a point where you kind of have the pieces that you want, but there's an extra piece that's here, and it's usually this kind of structural term, and you have to ask yourself, okay, is it the case that this thing is always small? Well, it's not small. So what do we do? Well, the conclusion here is, of course, then that this plain CBCMAC construction is not a secure variable input like the PRF. How do we address this? Well, there's one idea. The attack that we just gave exploits in a fundamental way the fact that we ask 2 queries, one, called x, that was 0 to the n, that's a prefix of the second query. Because our second query was 0 to the n concat t, where t was the thing returned by asking this. So x is a prefix of x prime. The first query is a prefix of the second query. So one approach would be to modify this plain CBCMAC construction so that you don't process the inputs directly, but instead what you do is you take the input x and you encode it in some way, and then take that encoded string and run it through CBCMAC. And in particular, if the encoding is prefix free, meaning no matter what 2 strings you put into encode, if you look at the output of encode on those 2 different strings, one is not a prefix of the other. That's what it means to be prefix free. All the outputs, no outputs from this will be prefixes of any other outputs of this. In fact, this works. If you were to analyze this construction, CBCMAC running on prefix-free encoded inputs, you would get a proof of security, because it turns out that this prefix attack, this prefix exploiting attack, is really the only attack, in the sense of distinguishing CBCMAC from a big random function. So this would give us a way forward. The problem is, in practice, almost nobody does that. And the reason why is that to make a prefix-free encoding, you have to basically see the entire input string, because the prefix could be, the first bit, or it could be all but one bit. You have to see the entire string to know how to encode in a way that's going to prevent any of those prefixes from appearing as possible outputs. So here's one example of a prefix-free encoding. If you were to take the whole message, buffer it up, and then prepend to the message it's the bit length of that string, this is prefix-free. And you can see that because if I have two X's that are different lengths, then in particular, this n-bit prefix of both of those strings will be different, which means that no two encoded strings X and X prime of different lengths can give you the same encoding. If they are same length strings, then while the first n bits of their encoding will be the same, they won't be the same here because otherwise they were the same strings to start with. So this is a prefix-free encoding. But in practice, this is not something you're going to want to do, in particular if you have long strings X, because you have to buffer up the entire string before you know what its length is. And you can't you can't release any of the encoding until you know the full length, because that has to go at the beginning. So prefix-free encoding, except for very specialized applications, for example, where you have short strings X and you can afford to buffer up the whole thing before you prepend the length. Prefix-free encoding is not a very practical way forward for general applications. So people don't do this despite the fact that it would work. But it does tell us something, and in particular the fact that making the inputs prefix-free allows us to get a proof of security suggests that if we could just find some way to not release the output of CBCMAC on prefixes of strings that we might care about, if we could just find a way to hide these internal values, which are the things that would be produced. Like if I just considered, this piece, if I considered this piece as the prefix of the whole message, if I could hide this value, then, maybe we could kill the prefix-free, the prefix exploiting property, and get security the same way we would if we had a prefix-free encoding. So this is the idea. And the way that we're going to hide any of these inner values for any prefix of any string is by just go ahead and computing CBCMAC with a first key, K1, as we did before, and take the resulting value and calling it T inner. And then this will then pass through one more call to the block cipher, but with a second key, K2. This is the eCBC construction. It's a two-keyed construction that runs CBCMAC and then makes one more block cipher call. If you're processing long messages, this one extra block cipher call is, it's not a big deal because, you're amortizing, it's one extra call over a whole bunch of calls. So it's not such a big deal. Having two keys is maybe more of a pain. Again, it depends on the application. But in any case, this is the enciphered eCBC construction with these two keys, K1 and K2. This is that. So basically, you run CBCMAC, you take its output, you make one more call. Well, all right. You can see that this is going to hide. If I were to say, try to mount that same attack and put in a block of zeros here, I won't see this value. Instead, what I'll see is this value run through this output and ciphering step. So I won't ever actually see T inner. So I can't then mount the same attack of taking that and making it the prefix of a string, to which I'll, if I take 0n and try to concatenate something here, I don't know what to concatenate because I never get to see this value. So that's the intuition behind breaking the attack, the concrete attack that we just described. More generally, it has the effect that I just mentioned, which is if I were to process some long string, then seeing the output of any prefix of that long string doesn't help me, at least in the attack. So, all right, let's say now we wanted to show that this construction is a good variable input length PRF under the assumption that E is a good fixed input length PRF. Can we do that? The answer is yes. It's going to require two steps. And let me try to motivate, just as a more general observation for you, what happens when you have a construction that has two different keys. We're using one underlying assumption, namely that E is a good PRF. That's supposed to be enough to bootstrap security for this whole construction. But if you think about the PRF security of E, that's with respect to one key, right? The oracle that you would get in the PRF experiment for E either has a secret key K, let's call it K1, or a random n-bit to n-bit function rho. But it's for one key, it's not for two keys. And you can't change the key in that oracle. It's just fixed by the PRF experiment. You're stuck with it. So anytime you have two keys, you should have in your head, I'm going to have to do two reductions, even though the thing that I'm looking at, the base assumption is that E is a good PRF. Even though I'm using one assumption, I'm using two keys. So I'm going to have two different reductions. One to take care of this secret key and change all of these E sub K1s into rows, which we'll call row 1. And then a separate one that's going to get rid of this key by having an oracle that's either E sub K2 for randomly chosen K2 or a random function row 2. Yeah? Anytime you see two keys, you're probably going to have to do two reductions. And that's the case here. So when faced with having to do two reductions, you can do either one first and just see where it goes. In this case, let's go ahead and try to get rid of all of these E sub K1s and replace them with random function row 1. And the way we're going to do that is by taking an adversary that breaks this thing and building from it an adversary that breaks these things, not this, but these things inside. So here's how we'll do it. As I said before, let's just do the obvious thing of saying, all right, if we were to build an adversary B1, and we're looking at breaking the PRF security of E when keyed with this secret key K1, which is randomly chosen, then we want to try to make it so that if the oracle that B1 gets is the real thing, if it is E sub K1, then we want to perfectly simulate this construction, the real construction. So when our oracle is real, we want to simulate the real thing. How do we do that? Well, we just pick a key K2 ourselves, uniformly at random. If you think about, be clear about this, if you were given an A that breaks, that distinguishes this big construction from a big random oracle with the same domain of strings, if you're given an A that was good at that experiment, what would happen in that experiment? The very first thing that would happen is two keys, K1 and K2, would be picked uniformly at random. Okay, so we're trying to properly simulate the PRF experiment for A in attacking this thing, because that's what A is supposedly good at. A is attacking ECBC with E under the hood. All right, so in that experiment, what would happen? K1 and K2 would be picked uniformly at random. Well, if our oracle up here is E sub K1, K1 would have been picked uniformly at random already by the enclosing experiment. So all we need to do is pick the second key uniformly at random. So we do that at first. Then we run A. When A queries some input X, then we simply first run CBCMAC using our oracle on the input X to produce T inner, right? We're going to produce T inner. Whatever this T inner value is, we're then going to locally run the block cipher, the function family. We're going to run E with the key K2 that we picked on T inner to produce T and return that back to A. And we finish by saying when A halts with some bit D, we're just going to return whatever A returns. Why does that work? So I had to take a little break in the video there because I realized I had a typo that I've corrected now. So back to where we were then. So we've built this adversary B1. It's trying to replace this thing, trying to basically distinguish this instantiation with key K1 of the underlying function family E from a random function row 1, given access to an adversary that breaks this thing here, distinguishes this from a big random function R with the same domain and the same range. So we built that B1 here, and we look at what happens if we were to drop this B1 into the PRF experiment for E. Well, if this oracle here is behaving as E sub K1, meaning the challenge bit in this PRF experiment that B1 is playing is 1, then what do? We perfectly simulate the CBCMAC construction. This is E sub k1. So we perfectly simulate this to make T inner, and then we send T inner through E sub k2 for a k2 that we chose uniformly at random, which means we've perfectly simulated for A an oracle for the ECBC construction with two randomly chosen keys, k1 chosen in our experiment and up here in the oracle, and k2 which we picked. Well, that is exactly what A expects in part of the game that it's supposed to be good at. If we look at the advantage that B1 gets, well, as before, we look at the probability that B1 wins the PRF experiment against E. When the challenge bit there is 1, that means that B1's oracle is E sub k1. As we just said, that means we perfectly simulate for A the ECBC construction with two randomly chosen keys. Since B1 outputs whatever A outputs, B1 outputs 1 precisely when A does. Since the challenge bit here is 1, the experiment returns 1 when B1 outputs the correct bit, which is 1, so these two probabilities are identical. For the other part of this conditional probability, so conditioning that B1 wins when the challenge bit is instead 0, we did as before 1 minus the probability of incorrectly guessing the bit being 0, in other words outputting a 1. So we get 1 minus the probability that A outputs 1, but now where the oracle is ECB, where rather than having E sub k1 up here, we have everywhere random function rho 1, because that's what we simulate if this oracle is rho 1. So that's the first part of B's conditional probability. That's the second part. And as before, if we take these two things and drop them into the full advantage expression for B1, we get the difference of these two probabilities. So in other words, B1 is going to be good at breaking E if A is good at distinguishing the proper ECBC construction from this modified ECBC construction where the inside block cipher is replaced by a random function. Yeah? So this will be large if A is good at distinguishing between these two kinds of oracles. We don't know if A is any good at distinguishing between those two kinds of oracles. We know it's good at distinguishing between this and a big random function. But in any case, the B1 we just built will have large advantage in attacking E if A is in fact good at distinguishing between these two kinds of oracles. So that takes care of this inner piece. How about this? What B2 are we going to build now to talk about the ability to break this? So to figure that out, we take these two terms here, and let's think about A's full advantage. So A's full advantage, recall, A is good at distinguishing ECBC with two randomly chosen keys from a big random function. That's what A is supposed to be good at. Well, if we do the 0 trick again, we take A's, whatever, this is the number, this is what we're told, right? A is good at this game, so this number is supposed to be big for this A that we've been handed. We're just going to add 0 to this number by adding and subtracting the same value. That value in particular being the probability that E, when provided the oracle that we just described a moment ago, where we have ECBC, but with E sub k1 replaced everywhere by rho 1, and a second random key, it looks like that's supposed to be a 2, it kind of looks like a 1. It's this thing, right? It's the construction of ECBC where the inner E sub k1s are all replaced by rho 1, and we still have this on the outside. So we've just inserted the probability that when provided with this oracle, A would output 1. We subtract that probability, and then we add that probability right back in. And what that allows us to do is to collect up terms. And in particular, if we look at this minus this, we just realized that that's exactly the pure advantage that this B1 that we built gets. So these two together will give us this thing we just talked about. What's left then is this minus this. In some ways, this is now becoming intuitive. If A is good at distinguishing proper ECBC from a big random function R, then what we're saying is, if this number's big, then either it's big because the difference of these two things is big, which is exactly the pure advantage that B1 gets, or the difference of these two things is big. Said another way, this number is large if replacing the inner block cipher with a random function allows us to suddenly realize, oh, we've been, we can distinguish that change. Either this number is big because you can tell that this change has been made. In that case, if you can tell that this change has been made, that we've replaced e sub k1 with a random function rho 1, well, then that gives us an adversary b1 that distinguishes e sub k1 from rho 1. Or you can distinguish between this construction, ECB, with now rho 1 everywhere inside of the CBCMAC part, but a proper key k2 and a big random function. Either you can tell this change has been made, or you can distinguish between these two things. That's what we're capturing here, right? If you can distinguish ECBC from a big random function, then either you break the block cipher as used inside of plain CBC mode, which is inside of CBC. Sorry, it's hard to say a bunch of times. Or there's still something wrong, yeah? Even when we replace the inner block cipher by its idealized version. So what we're going to do is say, well, okay, we'd really like to get to the point where we could get rid of e sub k2 as well and just think about structurally ECBC, this thing, but with all of these replaced by random functions, and then this replaced by another random function. That's really what we'd like to say, because that's the structural piece. So how do we do that? How do we get rid of the second key? We just basically play the zero trick again, and we add and subtract into here the same term, that term being the probability that if we provided A with an oracle not for ECBC rho 1 K2, but instead for ECBC rho 1 rho 2, we're going to add and subtract this probability. So we're adding 0 between, like in the middle here, and then collecting things up. Well, that helps us. Why? Because this piece is the structural piece we just talked about. This piece here, we could build an adversary B2 whose PRF advantage against E is the same as this difference of probabilities. And I'll let you think about what that B2 does, but we can sort of talk through it, and then you should try to write it down on your own. You need to build a B that, when provided an oracle in the PRF experiment for E, if that oracle is either E sub K2, where K2 is a randomly chosen key, or that oracle is a random function we're going to call rho 2, you want to simulate these two possible oracles for A. Well, how do you do that? You run A. When A asks an input X, you run CBC mode. You run this. But rather than calling an oracle, you simulate a random function, which you can do by lazy sampling. Basically, you just keep a table that says, okay, I'm going to keep I guess you have to keep a table because to lazily sample a random function rho 1, you're free to return any random value you want for every call to rho 1, so long as the inputs are not repeated. So you basically need to keep not the values that you've output, but just the values that you've seen so far in your simulation of rho 1. In fact, it's very likely that these inputs are not going to repeat, because if these inputs are uniformly random, if these outputs are uniformly random, then this is a random value and this is a random value and so on. And so until there's a collision among random values, you're never going to repeat anyway. So you're kind of free to just return random values here and keep track of when something goes wrong. So some intuition for how one would build such a B2, but in any case, you can build a B2 that simply simulates a random function rho 1, computes the inner part of the ECBC construction, which is just CBCMAC over that rho 1, and then uses its oracle for the output, uses its oracle for this. So if its oracle is E sub K2, then what we get is this thing with rho 1 everywhere with this on the output, which is precisely this. And if the oracle is instead rho 2, if it's row 2, then what you have is ECBC with row 1 used on the inside and row 2 used on the outside. And that's the piece that we inserted, right? So this you'll be able to upper bound by the proof advantage of an adversary B2. And then what we're left with is these two PRF terms, which has now gotten rid of both of the block cipher appearances in the construction. And we're left with the structural piece. If we replaced everywhere E sub k1 by row 1 and E sub k2 by row 2, and we look at, can A distinguish those two kinds of oracles apart? If this number is large, that means that there's something structurally wrong with ECBC. Turns out that's not the case. So if we look at this, we actually just sort of talk through this. Imagine that these two numbers are small, so we're hoping that this number is small. We want to argue that that's the case. And we're not going to do a proof, I'm just going to walk through the argument with you. What you observe is, this is the ECBC construction with row 1 and row 2, so it's this here. The observation is, this output value is uniformly random unless and until T inner is repeated. The input to row 2 is repeated. In other words, there's a collision on the output of CBCMAC over row 1. Absent a collision here, absent two inputs to CBCMAC over row 1 that produce the same T inner, absent that, every input to row 2 is distinct, which means every output is uniformly random. But that's exactly the behavior that you would expect from this big random oracle R. If you ask all distinct inputs to R, which you will because anything else would be pointless, the outputs of R will be all uniformly random n-bit strings. That's exactly how this construction will behave until you have a collision at the input to row 2. And so what this gives us then is that for all M and M prime that are queried to the oracle, such that T inner and T inner prime are not the same, then the output of this is exactly the same as the output of a big random function, right? So if it's the case that for every M and M prime that A queries to its oracle, which is either this or this, for every such M and M prime that are different, if it's always the case that for all of its queries, these values are distinct, then the probability, the A's ability to distinguish between these two is identically 0, because the output distribution from this construction is identical to the output distribution from a big random function. So really, all that's going to matter, and the ability to distinguish, all that's going to matter in this term here, this is going to be 0 unless A can ask two inputs that cause a collision here. So that tells us that this probability is upper bounded by the probability that, I put this in quotes because it's informal, that A manages as part of its queries to actually cause a T inner collision. So in some ways this should start to look kind of familiar, right? We're talking about, I've got something that takes in long strings, compresses them down to an n-bit string, and we're worried about whether or not the outputs have collisions in them prior to passing them into a random function. This should look like the thing we've already thought about. But in any case, what is the probability of making a collision here? If I ask a bunch of inputs to this big construction, what's the probability of getting a collision here? Well, again, informally, all of these inputs are going to be distinct because these are queries that A is asking to its oracle, and we know it doesn't repeat. So let's say that none of these inputs across all of those queries are repeats. In other words, across every query that A hands us, you end up calling row 1 on fresh points for every block. You could still get a collision here, right? You could still get a collision here just on the birthday paradox on the output of this. You could still get a collision here. Or what's more likely is that because you're allowed to ask messages of variable lengths, and they could be long, it's more likely you're only going to see, there's only going to be Q, if there are Q queries, there's only going to be Q possible values of T inner that are going to happen across all those queries. So the chance that you get a collision just by being unlucky on the output of this is like Q squared over 2 to the, you don't expect that probability to be large until somewhere around square root of 2 to the n, right? You're going to get a q squared over 2 to the n term. But there's a bigger term, because that analysis that we just gave assumed that there was never colliding inputs to row 1 across all the queries. If there's a colliding input to row 1 across queries or even within a query, then at some point, let's say that the value that appears here has been seen before by row 1, either within this chain of processing or in processing some previous input. If this value is repeated, this value is no longer random. And so what we're going to do, what we would do in the proof, is just kind of give up at that point and say, I can no longer claim that the input to the last block is random. And so I'm just going to kind of give up in the proof and say, if A is lucky enough that it asks two different inputs that cause at some point a collision to the input to row 1, I'm just going to say it wins, because it's because I don't know a nice clean way to do the rest of the analysis. If the collision is here, then this value is no longer random, but maybe the next one is, and you recover. But to avoid all of that ugliness, we would just kind of give up on the proof if we ever see the same input to row 1 across the queries that are asked. Well, so this piece of just getting unlucky, even though there's no repeats to row 1 anywhere, there you expect something like a q squared over 2 to the n term for the birthday bound. But you're actually not just going to see q values. So here you see q values of t inner, but how many possible outputs of row 1 do you have to consider, and thus inputs to row 1? Well, if there are sigma total blocks of inputs that you process, where sigma is the total bit length of all the queries divided by n, and take the ceiling, that means there are sigma times that row 1 is going to be called across all those queries. So there are sigma squared pairs of possible inputs, right? Within one query, it's, did this input and this input end up being the same? That's one pair. Or this input and the third input being the same? That's another pair, and so on. So there are sigma squared pairs, and each one of those sigma inputs is going to have a 1 and 2 to the n chance of colliding. So again, by the birthday paradox, we get it now a sigma squared over 2 to the n term. This is going to dominate q squared over 2 to the n because if they're all one block messages, then q and sigma are the same. But if some of the messages are much longer than one block, then it's going to become sigma that's really the dominant factor, not q. And so in fact, this is the bound that you get, that the PRF advantage in attacking ECBC, so let me scroll back up. The PRF advantage against this actual construction here is upper bounded by either you break the inner block ciphers in terms of being able to distinguish them from a random function row 1, or you don't manage that, and instead you have random functions here, but you break this outer one in terms of being a PRF. Or you can't do either of those. So far, we've got the PRF advantage of ECBC is equal to breaking the inner block cipher, or breaking the outer block cipher only, or breaking ECBC structurally. But we've just said you can't do that unless and until you see a collision here, and we're upper bounding collisions here by collisions anywhere inside, because that's the dominating term. I'm saying it's approximately equal. There's a constant that sits out in front here. It's a small constant. So essentially, ECBC is secure up to a birthday bound term in the number of blocks that are processed. And in particular, that means then that this thing stops looking, at least from the point of view of our analysis, this construction, ECBC, stops looking like a random function somewhere around the time that you've processed about 2 to the n over 2, so square root of 2 to the n blocks of message. So what does that mean? Well, if you're using a 128-bit block cipher, that means that before you've processed something like 2 to the 64 blocks of message, you should change those keys. That's what the analysis is telling us. That's a lot of blocks. So ECBC is indeed a good way to build a variable input length PRF out of a block cipher. and it's kind of salvaging CBCMAC, the thing we were hoping would work. It's salvaging it by wrapping its output in one extra call. And as I was saying, if you were just to replace, just kind of in your head, if you placed CBCMAC K1, so replaced in this orange box, with just some generic keyed function H with the same domain and range, so I'm replacing the particular internals here. Imagine erasing those. I've just got this orange box, and I call it H sub K1. Then this output here is, in fact, ECBC with 2 keys, so the original construction. So I guess what I'm really doing is replacing everything inside of this box. I just erase this and imagine this box is labeled H sub K1. Then this output is H sub K1 on M run through E sub K2. This is ECBC. But this should look really familiar because, in fact, this is precisely what we looked at in the previous video of having a hash function, a compressing function, although now with a secret key. And the analysis tells us, unless you can find a collision in this secretly keyed hash function on the inside, then the overall construction is a secure variable input length PRF. That's exactly what we looked at before, except there we didn't have a secretly keyed object. We said, okay, what could we do without a secret key, right? This is exactly the same construction, except now we're allowing the inside thing to have a secret key because block ciphers take secret keys. So this really, despite the fact that on the face of it, it's a very different kind of construction because it just starts from a block cipher. Really what we're doing is instantiating in a particular way the generic style of construction that we've already looked at of taking a hash function keyed in some way and then taking its output and running it through a fixed input length PRF. I did want to make one final note, and that is that if you're going to be processing lots of short messages, then making that one extra block cipher call maybe starts to pile up and become bothersome, because if you're, say, only ever processing messages that are like 2 blocks long, then your number of block cipher calls would be 2, except now you're adding one more, so you've got a 33% increase in the overall efficiency, the complexity of executing the thing, because you're making 3 block cipher calls instead of 2. So if you're going to be processing lots of short messages, you'd kind of like to do away with this output extra block cipher call. And it turns out you can. This construction, which is called XCBC or XOR CBCMAC, so we've got rid of that output enveloping block cipher call and replaced it by just XORing the second key directly into the last message block. So we got rid of it here. We just took that extra key and we now XOR it in here. This works too. The analysis is slightly more complicated, but you get a bound that's very similar, that the PRF advantage against XCBC is upper bounded by your ability to break this thing as a small PRF, plus a structural term, which is going to end up being exactly like before, some small constant times sigma squared over 2 to the n. So this works too without having to make the extra block cipher call. You still need 2 keys, which key management is almost always one of the hardest cryptographic engineering things that you have to deal with. So you'd kind of like to just have 1 key. And in fact, there is a construction which is standardized and used in a bunch of places called HMAC, which is a 1-key version of XCBC. You have to be a little careful. Basically, what you do in that construction is you take this construction, but the way in which you don't actually pick a second key K2, you generate it given just 1 key. And you generate it in a careful way, which I describe here in the text, but you generate this key in a careful way using the underlying block cipher. And you get a 1-key version. That's called HMAC, and HMAC is something that you'll see. So this sort of path we've gone through of saying, well, we started with something we'd like to say, we'd hope that this was a good variable input length PRF, but it's not. We fixed it by getting rid of the prefix sort of visibility problem by enveloping it here. We've got our first provably secure construction that's just from a block cipher. That block cipher call maybe, this is a good way to go if you're always processing long messages and can afford to have 2 keys. If you're processing some short messages, well then you can actually get away with not making that last call, just XORing the second key indirectly. And if you really can't deal with either having an extra block cipher call or having two keys for every instantiation of your variable input length PRF, then in fact you can get away with just having one key. So we started from the place that we thought might work, and we've come down to a place that's actually very efficient and used in practice and has one key and no extra block cipher call, this OMAC construction. All right, I'm going to pause here, and then we're going to pick up the story of HMAC. So CBCMAC, and then through its variations down to CBC, and finally XCBC and OMAC. This gives us a way to build a variable input length PRF straight from a block cipher, and only a block cipher. Let's talk about something called HMAC, or hash-based MAC. This is a very commonly used variable input length PRF for a variety of reasons, some of them historical. It's similar to CBCMAC in the sense that it starts from some off-the-shelf implementation. In the case of CBCMAC, it starts from an off-the-shelf implementation of a block cipher, say. HMAC, instead, is trying to build a variable input length PRF from a hash function, but using the hash function straight as it is off the shelf. And we've already looked at ways to build variable input length PRFs from a hash function that's collision resistant and a fixed input length PRF like a block cipher. The idea here is, well, right. So the idea here is, well, it's not clear from that high-level architecture that you can use things off the shelf the way you'd want to. HMAC was designed so that you could take any implementation of, when it first came out, MD5, which was a Merkle-Damgard iteration style construction with a particular fixed IV. You can take MD5, or you could take SHA-1 or SHA-256 or SHA-512, whatever. Take your off-the-shelf implementation, not mess with it at all, and turn it into a secretly keyed object that is a good variable input length PRF, right? We've talked about this early on, that if you have hash functions don't have secret keys because they're publicly computable. So you can't really talk about the PRF security of a hash function until you find a way to somehow embed a secret key into the hash function, and then you can start talking about it. So this is sort of the starting point for HMAC, and let's see, sort of follow the line of thinking here. All right, so here's our Merkle-Damgard iteration, and we've talked about this before, and we've talked about in particular the fact that if given a message M, you do a suffix-free encoding of M. So if you do a suffix-free encoding of M, we talked about suffix-free, for example, being to properly append the length, as opposed to prepend for prefix-free, append the length of the string to the end of it. So if you have any suffix-free encoding of your input M to produce a string X, then you process X by breaking it into appropriately sized blocks. And I think we talked about these being B bits and these being N bits. So you break X into B bit blocks, and starting from a fixed value IV, you then process using this compression function H, which maps B plus N bit strings to N bit strings. You iteratively call that to get your hash output. And you'll recall that we had this result that said, if this compression function is collision resistant, meaning you can't find pairs of things to put on these wires that result in the same output of the compression function. If this thing's collision resistant, then this iteration is collision resistant. Okay, but there's no obvious way to somehow bootstrap that result, that collision resistance of the compression function applies collision resistance of this, into, if I figure out a way to put a secret key in here, I get a variable input length PRF. Because on the face of it, collision resistance and behaving like a random function have nothing to do with each other. Certainly behaving like a random function would apply collision resistance, at least up to the birthday bound, but the other way, there's no particular reason to expect on the face of it that collision resistance tells us anything about the output distribution of hash values. Okay, so as I said, in a previous lecture, prior to SHA-3, all hash functions look like this under the hood. They are all Merkle-Damgard iterations, starting from a fixed IV. In fact, the IV is part of the description. So MD5 has a particular IV and a particular compression function. SHA-1, SHA-256, whatever, they have a particular IV and a particular compression function. So this thing is some fixed value. We'd like to be able to take some off-the-shelf implementation, just make a library call to say SHA-256, and via that library call, maybe some very lightweight pre and post processing, produce a secretly keyed thing that is a good variable input length PRF. Because if we already have an implementation of this and it's fast, then if we can do some lightweight processing of the input and output, say, we'd have something that was fast still, but now potentially a good secretly keyed PRF. Okay, so if you look at this thing and think, well, okay, let's say I wanted to stick a secret key in here. Where could I put it? I mean, there's only so many places, right? In fact, your two choices are essentially, I can put it in here on this wire at the beginning, or I can figure out some way to embed it into these blocks. Those are my only two options if I'm not going to change anything structurally. Well, if you're going to use an off-the-shelf implementation, you can't change this. This, SHA-256 has an IV. So this is actually fixed by the implementation. So really all you're getting to do is call on some string as input. So that's your only choice, is to somehow embed a key in here. So one first idea would be like, well, what if we put the key, say, in this first block? Put it here, right? We know the key up front. So in fact, we can actually pre-compute this value for any upcoming input. We can just, if we put the key here and then put our message in all the subsequent blocks, we could pre-compute this. And now when messages come in, we can immediately start processing by using this as kind of like IV prime, if you will, to process the thing. So that's a natural thing to try. Turns out that this construction doesn't work. So if you let f sub k of x be exactly that, h with k in the front followed by x, and you ask, is this thing a secure variable input length PRF, given in particular only that h is collision resistant? The answer is no. In particular, we have this problem. It's kind of related to the prefix-free attack we saw for CBCMAC. These are called length extension attacks. So essentially it's this. If I call this secretly keyed thing here on some string x, and I see the output, then because the compression function itself is not private, if I see the output of this construction on some input x, and I call the output y, so this is the output of my candidate. So I've got this candidate, secretly keyed thing that I'm hoping is a good variable input length PRF. I run it on some string x, I get a value y. Well, I can immediately compute locally h with y on this wire and any input I want up here. Why? Because I know y, I just got it. I know the description of h, so I can compute this value that's right here. But now consider if I took this picture. So let's say that I process some x. So here's my key, here's my x, and this value here is y. Well, now if I were to lift this and carry it up here, I have y coming in. I put whatever value I wanted here. I can locally compute this value. But that means then that I know what the output would be if I lifted this and put it up here, and I were to ask instead for the output of this secretly keyed construction on x concat with zeros. Because I know that the output of this thing is going to be exactly this value, right? If I made this key all x's and then put a 0 at the end, what I'm going to get is y with 0 coming in, just like here. I know this value. So I can predict the output of this construction on this new input, x concat 0, given only the output of the construction on some previous thing, x. This is called a length extension attack because effectively what I'm doing is I'm saying in fact, it doesn't matter what you do kind of before the end. If I know this value here, I can always extend it by an arbitrary string because I can always locally compute, given this value, what the extension would be for any thing I want to add here in that processing chain. So length extension attacks let us break this construction quite quickly. You could consider, for example, putting the key at the end. That, in fact, will work, but it has its own problems in practice. But the fundamental thing here, like in the case of CBCMAC, where we had these prefix exploiting attacks, here we have these length extension attacks. And we'd like to at least stop those. And in fact, it turns out that stopping length extension attacks is all one needs to do. That's really the only weakness of this thing. So let's think about how we would stop these length extension attacks using an off-the-shelf. We still want to use the off-the-shelf implementation. That's exactly what HMAC does. So here's the whole HMAC construction. And I've drawn it up here, and then we're going to break it into smaller pieces. Here's the idea. We wanted to put the key at the beginning because it was easy. It would allow us to pre-compute this thing and then use it, subsequently for lots of processing. So we are going to put in something closely related to the public key in this first block. We're going to process it using our off-the-shelf implementation. But rather than releasing this value, as we would have done before, we're going to take it. We're going to run it into the compression function, like another compression function call. And we're going to call this last compression function on an input that is itself created by, again, the secret key K, but now with a different XOR value. So here it was P1 and here it's P2. In the actual standard, this is called, I believe, IPAD for inner padding, and this is OPAD for outer padding. They're just fixed constant strings that are part of the HMAC description. So the whole construction is I make something related to the key. I do the thing I just tried to do. Then I'm going to hide the output behind another secretly keyed thing in order to hide this value. Okay, why this sort of funky construction like this? In particular, why this extra piece here? Because if you didn't have this, this would start to look an awful lot like what we just did for CBCMAC of having some inner thing whose value is hidden behind some outer thing. Well, the reason this is here is because, keep in mind, we want to use the off-the-shelf implementation of, say, SHA-256. So if you note that this construction is calling, it's calling the big hash function twice. So if you think of H as being SHA-256, what are we doing? We're calling SHA-256 on this input. That's here. Then, well, we have to encode it as a b-bit string. Then we're calling H again, SHA-256 again, but now on this two-block message, if you will. The first block is this secret key piece. The second block is the output of the inner processing. So I want to be clear here. You do call, say, SHA-256 twice, but you only call it once on the long input. The second time you call it, you're calling it on a two-block input. So if you're processing long things, this extra call to SHA-256 is kind of for free because it's going to be extremely fast compared to the computation of this inner piece. So we use the off-the-shelf implementation. Notice here, it's just the thing, right? It's the IV, and then you process whatever input you provide me. So I'm calling SHA-256 on this input here, and then I'm calling it a second time on this input. So I'm using the off-the-shelf implementation. And as I said, it's effectively, if X is long, then it's effectively the same cost as just calling SHA-256 once. Okay, why should this be any good? Why should this work as a variable input like the PRF? And notice it has a single key even. Here's kind of the intuition for it. So observe that, pull it here. So length extension attacks exploited the fact that we could see this inner value even though we had a secret key up front, right? And we're hiding now. We're hiding that value behind this compression function call that you can think about is being keyed itself. In particular, it's being keyed by the output of this first call here, which consumes the secret key. Okay, so I've drawn some boxes here. We've got the whole construction. The whole construction here, remove the box. The whole construction is HMAC with key K, right? The magenta colored box here is sort of a subconstruction that people refer to as NMAC, or it's called nested MAC. it takes two keys. So think about this magenta box. Forget about this. Forget about this. Just the magenta box. And imagine that that thing is keyed on the chaining value through with a key K1 that's been picked uniformly, and here with a key K2 that has been picked uniformly. So this magenta box keyed by this two-part key processing the input X. This is NMAC with two keys on X. Okay, here's the way that the proof intuition goes. First, try to show that NMAC with these two keys is a good variable input length PRF. If I were to build this thing, so notice I can no longer use an off-the-shelf implementation because I have to change the IV in two places, in fact, to be secret keys. But just as a thought experiment, imagine somebody built this thing. Would it be a good variable input length PRF? Well, if you look at NMAC, this thing you can break into two pieces. One is what's inside this orange box, which I'll call H tilde inner, using key K1. This orange box here is a hash function. It's the hash function that we started with, but where we've now given ourselves access to the IV and replaced it with a secret key K1. So the output of this is this thing. NMAC is a good variable input length PRF if this H tilde inner thing is epsilon almost universal over a random choice of K1. And this last compression function call, if H is a PRF when secretly keyed through this wire here for a random key K, if this is a good PRF when keyed through here, so it's a B bit to N bit mapping where the key is N bits long, if this thing is a good PRF, in particular a fixed input length PRF because the input is B bits, right? So if this is a good fixed input length PRF, and this thing inside this orange box is epsilon almost universal, does that look familiar? It's an epsilon almost universal hash function being fed into a fixed input length PRF. That's how you prove that NMAC with two keys is a good variable input length PRF. That's step one, and it's just using what you already know. Okay, but how do we get from NMAC to HMAC, which is this whole picture? Well, NMAC needed two random keys to work. But we don't actually have a way to mess with the IV, so instead we think of the first compression function call on each piece of HMAC, the whole construction, these and these two together. If we think of these as functions, so here I've called this F1 sub k, so this is F1 sub k. If we define this to be H with k XORed with this public string P1 on this wire, if we were to define a function to be H with this on its first wire and anything on this wire, that's our function F1. If F1 is a PRF on the single input, the IV, we only need for that construction for a secret key K to have random looking outputs for this one input. If that's the case, then K1 is indistinguishable from uniformly random. So this thing actually generates for us a key K1. And it will be secret because this is secret. And if we call this thing here F2 is again H, but now using the secret key XORed with this public P2 and anything on this wire, that's our F2. If this thing is a good PRF on, again, the single input point IV, then this thing is indistinguishable from a uniformly random string. Together, that means we get, under the assumption that this is a good PRF and this is a good PRF on this one input, then that says the first call here actually creates a secret uniform random key for H inner, and this creates a uniform random secret key for this last compression function call, which is exactly what we needed for this. And so the combination of those things, this being a PRF on one input, this being a PRF on one input, and this being epsilon universal, that's all we need to get the whole thing together. If that doesn't make sense, roll it back and let's do it again, that we take the variable input length PRF security of NMAC, the thing in the magenta box, and we combine it with this very weak PRF property on these compression functions, meaning on one point. Those two things together give us that HMAC, the whole construction with a single key, is in fact a secure variable input length PRF. It's a very cute idea. It provides a way to use an off-the-shelf implementation. Again, I want to stress that fact that really when you reconnect all these wires back into the, where's the picture? Here it is. When you reconnect all those wires back up, what do? You call SHA-256 twice. Once with the secret key and the message, so that's the expensive piece. You take that output, you call SHA-256 again with the key in the first block and the output of the previous call in the second block. So this is a very quick call to SHA-256 to make HMAC. So we can use an off-the-shelf implementation of, say, SHA-256, a single key, and under some relatively mild assumptions, we can prove that HMAC is a secure variable input length PRF. Because hash functions are fast, and because this lets you use off-the-shelf implementations of existing hash functions, and because it uses only a secret key, HMAC is a very, very commonly used variable input length PRF, probably the most commonly used. And we'll run into this again in the next lecture when we start looking at what key derivation means, how key derivation functions work. This is something that's quite important in modern secure channel protocols like TLS, whereby you don't have a secret key to start from. You have some exchange that at the end of which you hope that you both now, the two parties, share some, have some shared randomness that they believe to be secret, that only known to them. But then you want to take this thing, it may not be a fully random string that you two now share, so you run it through something called a key derivation function, which in effect squeezes out any randomness that's in the string that you provided into a shorter string that is in fact indistinguishable from random bits. And now you can use that to start keying things like underlying encryption schemes. So key derivation functions are one very important and very common use of the HMAC construction, and we'll see that in the next lecture.